Okay guys, so we all know that equimolar counter-diffusion doesn't always happen for gas phase or mass transfer. So we have here the diffusion A through stagnant or non-diffusing B. Let us look at this the figures again. So this is the figure for the equimolar counter-diffusion, while this is the figure for the diffusion of A through stagnant or non-diffusing B. So we would observe that they would almost have the same graph or same figure. So the only difference is that both has P, which represents the bulk phase compositions, and M, which represents the interface compositions. However, we should note that the slope PM of the line segment PM is different for those two cases. So the slope again let me just repeat what Ben said earlier, that the slope for the equimolar counter-diffusion is given by the equation negative K prime X over K prime Y, while the slope for the diffusion of A to stagnant B or liquid phase B is the slope of negative K prime X over 1 minus XA I to the M IM over K prime Y over YA IM. So the diffusion of A to stagnant or non-diffusing B is the common case for what usually happens in mass transfer. So the equation of the diffusion of A through a stagnant gas and then through a stagnant liquid is given by the equation given by the equation Na, which is flux, is equal to Ky YAG minus YAI, which is also equal to Kx XAI minus XAL. Now Ky here is given by another equation. Ky and Kx are given by another set of equations, K prime Y over 1 minus XA IM, while Kx is equal to K prime X over 1 minus XA IM. The manipulation of these equations gives the slope of the line of, again, line segment PM. Okay, the equation where 1 minus YA IM is equal to 1 minus YAI minus 1 minus YAG over the ln of 1 minus the natural logarithm of 1 minus YAI over 1 minus YAG, and 1 minus XAIM is given by the equation 1 minus XAL minus 1 minus XAI over the natural logarithm of 1 minus XAL over 1 minus XAI. So the equation will be transformed into the equation 8 given by the slide. So Na is equal, this flux is equal to K prime Y over 1 minus YA IN times YAG minus YAI, which is also equal to K prime X over 1 minus XA IN times XAI minus XAL. Rearranging the equation would give you equation 9. Now, this equation 9, the slope of the line PM in figure 6 again, to obtain the interface composition is given by the left-hand side of the equation. This differs from the slope from the equimolar counter-diffusion. This is different by the terms of 1 minus YAIM, which is this, and 1 minus XAIM. When A is diffusing through stagnant B and the solutions are dilute, 1 minus YAIM and XAIM are close to 1. Okay, so what do we need for this from what I have discussed? So the slope can be determined by iteration, and again the threaded trial and error method should be used and is summarized here. So assume 1 minus XAIM and 1 minus YAIM to be equal to 0. The slope and the values of XA and YA are then determined. The values of XA XAI and YAI are used to determine the slope and the new values of XAI and YAI and then are then computed. The new slope of the lines determined in the process is continued until the interface compositions do not change. So, just to clarify these things, we assume first XAI and YAI, and then we input this in the previous equations, and then we will get another set of XAI and YAI. The moment we arrive at the same or constant slope, or we get from the computation we get the constant slope at least three consecutive times we can use this. So then we will know the slope and the compositions.
So the very big question for today is naintindihan ko ba yung pinidiscuss namin? And so, para mas maintindihan nyo, magtatagalog na lang ako. And we will have this sample problem for the mass transport. So, we will have the yung first sample problem. So, guys, pwede nyo bang basahin para sa akin yung first problem? Generally. Malabo pa. Si ano na lang? Pao.
The solute A is being absorbed from a gas mixture of A and B in a wetted wall tower with liquid flowing as a film downward along the wall. At a certain point in the tower, the bulk gas concentration YA net is equal to YAG is equal to 0.13 mole, 38 mole fraction. And the bulk liquid concentration is XAN is equal to 0.1. The tower is operating at 298 Kelvin and 1.01 times 10 to the 5th Pascal. And the equilibrium rate are as follows. Solute A diffuses to stagnant B in the gas phase and then to a non-diffusing liquid. Using correlations for dilute solutions in wetted wall towers, it was predicted that Ky equals 1.465 times 10 to the negative 3 kilogram mole A per second meter squared mole fraction. K what X was 1.97 times 10 to the negative 3 kilogram mole A per second meter squared mole fraction.
Thank you, Pa, for the reading. Yeah.